I will be also here in July, and something that I discussed in July, I'm insisting and telling you again. And the title is different, Brine, Mine, Nexus. And let me make a couple of statements. This title means that in my personal opinion, the water industry has much more responsibility than just producing water. And that's the first point. Much brighter opportunities and potentiality than just selling fresh water. The second one is that in the last 25, 30 years, a lot of quite interesting work has been done around the world in optimizing and solving problems related to water production. So everybody is familiar with water stress. And we heard from the plenary this morning already that water stress is a problem, still exists, will exist in the future, but significant amount of progress has been done. These numbers, you are familiar, you know what is going. Most part, water is the most present product on Earth, by the way. But salty water, fresh water, the one we need more, is absent. And more than this, you learn from the plenary this morning, 70% of the water that we are producing today is going to agriculture, which means today in the country growing, India, Africa, etc., where agriculture is becoming means food, a lot of water is going there, and the salty water is not appropriate not only for drinking for humans but also in agriculture. And the possibility to have a solution, however, exists. And you see the trend in the last year, you saw it this morning, significant success of membrane technology that at my time, when I was a student, as most of you, membrane were not existing as an industrial application. Basically, it was 1 to 3%. Today, you see, starting from the 2000, that means from this millennium, membrane technology is becoming a dominant technology. Progress can be done, but keep in mind that already we had a lot of success as a researcher in producing better membrane, in increasing permeability, in controlling fouling, also biofouling, etc. So a lot of good work has been done, not easy to make breakthrough. I don't expect any new membrane in the next few years, particularly in the reverse osmosis and similar. The system, optimization of the system can be still interesting, but that means a lot of effort and a lot of money. On the contrary, remember that we had big success, but there are still problems that have not been solved and cannot be solved. With the traditional membrane operation, that means osmotic operations, as a reverse osmosis or nanofiltration, these numbers are already some of the best numbers available. That means the recovery factor for the water you are going to produce is about 50%. If you were reading this slide this morning, you saw in a single case that the speaker was telling all the rest was going back to the sea. So you lose 50% of the raw material on which you are working, which is not very efficient in a process engineering approach. You still can have, you would like to have recovery factor not 50%, at 95% if possible. And we need this level of recovery factor. No way, don't spend your time trying to solve the problem with osmotic process as reverse osmosis. It's a thermodynamic balance that will tell you that very, very difficult. You cannot operate at the 500, 1000 atmosphere, etc. No way. So there are some limits. And which is not energy consumption. Energy consumption, we already made significant progress, and the system is nicely approaching not the theoretical, but very good value. So the problem that we have to face now is to change the approach. And to change the approach, there are two motivations. One I was telling, nothing better than what has been done until now, really better, can be done using this kind of technology. That means osmotic phenomena, which means hydrophilic dense membranes, the ones that are on the market today. If you look at the system that has been present in this line, that was a project we had in Europe. I was coordinating about 5-10 years ago, called Medina, by the way. And it was the first time which we were suggesting not using membranes only in the pre-treatment, but using membranes also in the post-treatment of our reverse osmosis units. Because if you introduce some new technology, not osmotic operation, but totally different, where there are no limits, for example, in terms of the concentration of the salts affecting, killing the transmembrane flux as in osmotic phenomena, the possibility to increase the recovery factor was significant. And that is related to another point very important. So this, you see, this is the flow sheet of Medina. In Medina, what we were telling is to be careful. If, when you have reverse osmosis, if you introduce new technology on the concentrate of the different RO or NF plant, and this system can be membrane distillation, membrane crystallizer, and similar, you can produce energy, pressure retarded osmosis, reverse electrodialysis, and you can produce salts. You can increase the recovery factor. Why this is becoming important? This is becoming important because you have to realize that today we have another stress that you don't see in TV, is not yet written in big terms on the newspaper, so large public does not know. But if you make a little bit of research on the web, you will realize that in the last 100 years, all around the world, we had a depletion, disappearing between 75%, 85% of most part of the minerals from the place where they were normally extracted. And people are not aware of this because nobody was taking care. You are extracting something, using and discharging as a waste. Today, we realize that in a relatively short time, most part of the minerals which are controlling our industrial development, the innovative industrial development, that means these chips, computer, plasma, new catalysts, etc., basically are disappearing if we don't take care of the situation. Where are all this stuff? All this stuff is here. No, the ocean, the place where we are, the seawater we are using for producing fresh water, is the most interesting open sky mine today available on Earth, where we have been discharging in the last 1,000 years, and recently in the last 100 years when we started to use more and more the minerals without taking care of their reuse. They are just there. So the problem is, why don't we try to consider that in desalination, don't watch only the permanent, which costs nothing, by the way. Water has no value, or very marginal value. People will never make profit on water. They are trying to do it. Public will react and will say, no, I don't want to pay for water. Nobody will complain if you will react and you will ask money for the concentrate where minerals are present, or for the energy that eventually we can produce. Now, if you are looking to the situation that you can find in the literature, you will find all the different kinds of minerals which are present in the water. A lot, basically everything. In some case, very large concentration, in some case, minor concentration. The situation is very clear. Somebody, Professor Sean, was already anticipating some of these data. You can see here we are working to identify, and this is not our data, but our data that you can find the reference from the Geographic Institute in the United Nations, or some geographical studies in the United States, etc. We have, for any minerals, the amount that is still there, the amount we are using per year in our today industrial activities, and that means how long this mineral will be still available. And if you do this, you will see that in many cases, these minerals have not been elaborated and updated to the normalized or the growth in consumption. All this number can be, the situation can be much worse than the one we are describing now. And to the point that if you go today in the traditional Mendeleev table published by the American Chemical Society, I will always mention that at my time when I was a student, everything was black and white. Today is no more black and white. It's black, white, and blue, yellow, red, etc. because each color is telling you for how long this mineral will still be available if we don't take care of the problem. And most of them are just minerals that are just very important for our industrial development. Membrane system can do much more than just separation of fresh water from salts. Membrane system, not the traditional one, the one not yet dominant technology as reverse osmosis or nanofiltration similar, can offer solution to this kind of problem. The most interesting operation, what we call membrane distillation and related problems. Membrane distillation is a process in which basically transmembrane flux is basically independent from the concentration of the feed. Just the opposite that you have in reverse osmosis. When you concentrate the feed, flux are going down to the point that you approach at zero at one point. When the concentration is too high, if you don't change the pressure, flux is going to zero. It does not happen in membrane distillation, and that you can easily understand if you go through what is membrane distillation, which means that in membrane distillation, we not only can separate salt from water, but we can concentrate the brine to the point that we can induce a supersaturated solution on the brine side. That means we can induce heterogeneous nucleation, which is a controlling step for crystallization. Now, crystallization is an old chemical operation, the most interesting for separation of minerals, for the purification of minerals, for the concentration of minerals. So ideal for trying to give a contribution to the problem I was mentioning before. And that's what we are doing today. Quickly, I'm going through this, but you can find in the literature most part of this data is published. The point is here that the driving force in crystallization is just the difference in the vapor pressure across the membrane. And as I was mentioning before, it's nothing more than membrane distillation, in which you have a traditional loop of a membrane distillation step, where you can concentrate as much as possible the brine, but if you want to arrive to crystallization, that means if you want to produce crystals, you must be also able to separate continuously the crystal from the loop in such a way you don't plug, you don't make huge, bring too much mass resistance in the system, so you have to remove this. So the only variation and the only part that you have to study carefully is this one, how to induce heterogeneous crystallization in the membrane module, but the growth of the crystal has to take place in different parts of the system in such a way to minimize. Seems to be difficult, is not. Today, a lot of people are working with this system around the world, and if you know what you're doing, you will see that can be done. Crystals, in some cases, help you to control fouling. When crystal, not gel, they are just inducing, they promote turbulence locally, and that is a way to minimize concentration polarization eventually with no big trouble. But anyway, this kind of system can be done, and so you can realize this membrane distillation with the appropriate configuration in such a way that the crystals are removed, so you can crystallize basically in organic molecules, organic and enzyme protein, the big protein. And that is one of the kind of work that was mentioned we are doing. There is a lot of problems to be solved. I just quickly show you some of them. Basically, you can realize this in different ways. You can create a vapor pressure gradient by changing the temperature, traditional membrane distillation, or by concentration different, what we call osmotic membrane distillation. And you can combine the two eventually. Both of them can help you to create a supersaturated solution, and the supersaturated solution will induce nucleation and crystal growth. What is important here is not only you have crystallization, but this is a way, in principle already, where you can crystallize in a much easier and interesting way than normal crystallization. If you go in the literature, in the paper already published, you will find the description of the fact that, in principle, membrane is a place in which, if you have an ideal membrane, we are using always hollow fiber, and hollow fiber has this one, you see each pore that you have in the system, assuming they are all equal and parallel, is a place where you can induce crystallization. So you have basically a very homogeneous distribution of the metastable phase where heterogeneous nucleation is supposed to take place. Very different from the situation that you can have in real life, in traditional system. You have to take care also here of concentration polarization phenomena, but more than this, in temperature polarization phenomena, which are the real problem, because also in this case you can have temperature at the interface and concentration at the interface that can affect the system. Now, concentration is negligible, does not affect the driving force very much, but affects the viscosity, so you have to take care of the increasing viscosity. Temperature polarization can be very, very significant. Very, very significant. You have to take care of two problems. One is the concentration, temperature profile that you create on your membrane, but also on what happens in the material that you are using. Until now, when you're talking about reverse osmosis, nobody's asking you thermal conductivity of your membranes. It's a parameter not present in any study that you have on the reverse osmosis membrane. In here, you have to look about the thermal conductivity. Today, we are losing about 50% of the energy you supply to the system, not in warming up the solution and creating vapor, but in warming up the polymer. And if it has high thermal conductivity, you are losing a lot of energy just warming up the polymer that we don't need, so this is lost. So you have to look materials with appropriate material, appropriate thermal conductivity, appropriate porosity, appropriate morphology of the pore distribution, etc., to keep control of temperature polarization phenomena, which are a little bit more complicated than just concentration polarization. But any good PhD student in chemical engineering will give you just the answer and will be able to solve the problem. If you do this, you can produce, using this heterogeneous nucleation, some of the best crystals today produced on Earth. These are the crystals and protein that if you go and you find in the literature the results, these are better than the crystal we are producing in the space lab in a microgravity environment. So excellent situation to the point that this has been published in, assuming that what you are able to create when you have a membrane and you have a nice surface morphology, what is happening here that you have some cavity on the surface. Now having this cavity, when you make the solution going through, you can concentrate the protein at level in these cavities, impossible to be reached in the free solution, no way. So people were not able to build this. In membranes you can do it. You can do it this kind of, using this kind of special case, and related also to the value of the hydrophobic character of your membrane, and that can affect a lot the system, can affect a lot also in terms of the traditional nucleation rate. You can use traditional equation introducing the appropriate parameter related to the porosity, morphology of the membrane, etc. And at the end, you can have interesting this plot where you plot delta G heterogeneous compared to the one homogeneous as function of the contact angle. You have this behavior that we will not have time, but later on, if you take the theoretical analysis, you will see that these data are perfectly coincident with theoretical one that you can extrapolate, and including the level of porosity of the different membrane that can also affect this kind of value, which means that you have an influence. If you change the activation energy, basically, you are changing the kinetic, the growth of your crystals. All the data here are telling you that these are all protein basically, or amino acid. And when you see here, I don't know, 12 hour or 1 week, etc., means that in literature, the expectation was 2 months, and you can crystallize in 2 weeks. The expectation was 1 week, and you crystallize in 2 hours. So if you check all these nice figures, and this is kind of the motivation for showing you this result. That's the one. This is trypsin, this is lysine. Now, this was initially done for organic biomolecules. A lot of interest in pharmaceutical application, big molecules, etc. But today we have different interests. All this data telling you that the quality of this crystal is excellent. And you see here the variance here, that means that all these crystals are equal. If you just make with traditional crystallization, you spread the frequency of the ratio between the size of the molecules in a large spectrum, and when you do with membrane, the variance basically they are mono-dispersed practically. This is if you go to the synchrotron and you check the quality of this crystal, as I was mentioning, is an excellent refracting power crystal from the membrane system, much more than what you can have in other case. Don't worry about the problem of fouling. You can find data in literature showing you can work for months producing water as a permanate and crystals as a concentrate. 6 months, 8 months is our term of operation, basically. So quite interesting. You can control the kinetics, etc., etc. I would like to show you in the few minutes that I still have available the 2 more important parts of the story. First of all, you not only produce crystals, but you can handle the system producing specific polymorph of the material you're looking for. This is an amino acid, glycine, and glycine can exist in the form alpha, beta, gamma, different polymorphs. Today, if you go in literature, you can find the data. We are able to produce with membrane-assisted crystallizers not glycine, but the specific alpha, beta, or gamma form, just working on the parameters controlling the system, basically on the cross-flow velocity and transmembrane pressure and temperature. Doing this, you can find data if you can produce just gamma or just alpha, the 2 most interesting ones. And that's the same. These I think is paracetamol. Yeah, paracetamol is 2 different forms, just changing the classic parameters of the system and looking to the property of the concentrate. Forget about the water. Nobody is looking to the water that you're going through in this kind of case. And that can be done in many different ways. You can produce specific kind of, and we are trying to give an explanation about this, and there's a lot of interesting explanation in progress, not easy. It's a little bit naive, but basically we are extracting and removing from the system some of the intermediate kinetic form that you can crystallize and normally they disappear, but if you extract from the system, avoiding growing crystals, you never arrive to the thermodynamic form, and you can produce some of the intermediate form, the one that you can be eventually interested. And again here, you see that this is for a few hours, but basically the transmembrane flux is no evidence of flux decay. If you do the same in reverse osmosis, at this time you are basically out. Just to tell you that now this system is no more working on organic. This system is working today on desalination. The big project in which we are assuming that you can extract minerals from the brine that I was describing before. Keep in mind that the brine of the RO plant existing today and running around the world, you can, if you just extract magnesium from the existing brine today, you can increase production of magnesium 100%. You can double the industrial production of magnesium. With lithium, that somebody was mentioned today, just extracting lithium from the brine of the existing RO plant, Ashelon, Solek, etc., you can increase 30% lithium production, etc., for any kind of mineral, something can be done. However, it's not so easy. Just to show you, and I will stop the last one case in just talking about, this is the case I was mentioning before. In total, the conclusion of Medina, you can just purify, we can work with a recovery factor of about 92%, basically, but you can produce the fresh water and minerals. And that can be the nice way to reduce the cost of water production. Minerals is value. water is cost of zero, and people don't like to pay for water. And nobody will complain if you sell him lithium, magnesium, boron, uranium, etc., etc. Just to show you that a lot of work is in progress today. First, to solve problem. Look at this case here. If you want to extract lithium from the sea, try, and you will not have any success. You see here, lithium at the 50 degrees centigrade will have a supersaturated solution that we can crystallize at 14 molar solution. You will never be able, using traditional direct contact membrane distillation, the most normal one, to arrive this concentration. You go to zero flux at 10 molar, 9 molar, so no crystallization. But if you have a smart PhD student and you start working and we try to understand what is going on and to check what is inducing this phenomenon, you will understand there's a typical example of wetting that is not appropriate the configuration you're going to use. If you change configuration, no more direct contact membrane distillation, and if you go to vacuum membrane distillation, and you can understand why if you're an expert in membrane distillation, you can see that you can approach easily the 14 molar and still you have transmembrane back. So you can produce crystals of lithium chloride. By the way, today they extract normally carbonate, lithium carbonate. In the future, lithium chloride is becoming more interesting than lithium carbonate in the fuel cell application. You can see here you can have a nice crystal of lithium carbonate, and in some temperature you can have two polymers. In some temperature you have only one. Increasing temperature you only produce one form, and decreasing two forms. But you have to use a vacuum membrane distillation, not direct contact membrane distillation, as I was showing before. So not easy. You need a lot of specific experience in this operation that people don't know. They don't know the operation, but they don't know also the membranes. These membranes are hydrophobic, not hydrophilic. Everybody producing water today is using hydrophilic membrane. If you have a polymer hydrophobic, they tell your professor will tell you make hydrophilic. Find a way to change the property making hydrophilic. Don't do it. Try to emphasize the hydrophobic character and make hydrophobic porous membrane, and you can operate in this kind of system. And that's why we are working with ceramic membrane. We are working with Professor Sean and colleagues in Taiwan with some other kind of membrane, but we have to make everything hydrophobic, not hydrophilic, which is not easy. But if you do it, this is just with the membrane from Professor Sean, nice lithium chloride, very clean in the appropriate mono form, not the mixture of different polymers, but specific ones, quite interesting for industrial possible application, etc., etc. This one just telling you that if you do this, you'll change the way you write your table. The way to save money, forget about energy consumption, forget about the pressure recovery, etc. Because if you do right, total annual profit for the salts, forget about the water. You are producing money, just producing minerals. So don't complain about brine disposal. Don't send back 50% in the ocean, but just optimize in terms of the production of the concentrate upstream your membranes. And on the side, you make a present to the people and give water for drinking and for agriculture. But the real final benefit is this water, this number here. And in principle, this is a big number. This number will change 100 times because we are a professor, so there is a lot of other parameters that you have to count, but this is the logic. If you want to change significantly, not small improvements, etc., the final cost of water production, the best way of doing it, don't try to improve RO, etc., because a lot of work has already been done. It can be done, but will be marginal. Change completely your mind. You can still produce fresh water, but you can decrease the price having no brine disposal problem, but having something to sell. And that can be today more and more real value, and shortly you will read also newspaper telling problem of not water stress, but the mineral stress. And something happening already with China about the rare earths, etc. We're fighting it already when Mr. Trump told the people, I don't give you, I increase it, etc. They say, I don't sell you anymore the mineral, the rare earths. That was a big confining because they are the producer of these things. And if you don't produce this, you can have a significant problem in a lot of advanced technology. This can be a way to recover all the rare earths which are in the sea, where we have been discharging in the last 100 years. Sorry that there is a lot of things that can be done here in producing new kind of membrane. No more tradition. That has to be hydrophobic materials and well controlled in the porosity and morphology. So we are looking to totally different graphene oxide, and 2D. There's a lot of salts that people never been used for making membranes. Telluride, bismuth, telluride, etc., unknown to me, and I am a professor of chemistry until recently. And this material can give quite interesting contribution to change the story, not in terms of flux, but in terms, this is bismuth calcogenide, in terms of crystallization. You can see here, what we want to control is the growth of the crystals and the quality of your crystals. And with this kind of material, compared to the traditional membrane in PVDF, you can just have significant change in positive. So a lot of work to be done, not existing today in the literature. So students have to pay a little bit more attention what is going on and change the approach. Don't make a bad process where you lose 50% of the raw materials, brine disposal. Make a process, combine, you cannot change a single step. Make a system where you combine the traditional RO with other membrane operation that can help you to arrive to 95, we are working 93 recovery factor, and that can help also in the final cost of water. Thank you for your attention.
Yes.